Good afternoon, doctors. We are Group 1. Our group member consists of Lin Yongying, Ip Sian, Sun Huisin, Abdul Hadi, and Chang Kakian. And I am Chang Kakian. So I'm going to talk about task 1, which is Laplace transform of series RLC and parallel RLC. As we can see, for series RLC, we change the Laplace transform of VR is R, while we use the Laplace transform of first derivative to get the VL is LS, and the Laplace transform of integral to get VC equals to 1 over C integrate IT dt. So it's 1 over CS lah. So and then we do some modification, and then we get 1 over LCS squared plus RCS plus 1. Well, for parallel, it's the same. Yeah, we get IR equal, but we just change the VR to I, change voltage to current for parallel. So for IR is 1 over R, for IL is 1 over SL, for C is SC. So, and then we do some modification, we get S over C bracket S squared plus 1 over RCS plus 1 over LC.
For the series RLC circuit with a step input, capacitor voltage shows underdamped behavior with 46.84% overshoot and a testing time of 0.0782 seconds. The oscillatory response is due to complex conjugate poles as energy exchanges between the inductor and capacitor. The FFT confirms broadband frequency content typical of transient signal. Under a sine input, the series RLC acts as a bandpass filter. The output peaks at 1.1668 volts, showing resonance amplification. The waveform is smoother, allowing signals near the resonant frequency to pass. This is supported by the FFT and baud plot showing a dominant frequency. With a pulse input, the circuit shows sharp transients and ringing, confirming its underdamped nature. The peak reaches 1.4686 volt, indicating sensitivity to rapid changes. The FFT shows a wide frequency spectrum, consistent with the pulse broad frequency content. For the parallel RLC, the response is overdamped. The capacitor charges quickly with a rise time of 0.0173 second, 0% overshoot and setting time of just 0.0308 second, reaching 1 volt. This reflects higher stability and energy efficiency. The FFT shows low frequency dominance. With a sine input, the parallel RLC behaves like a bandstop or low-pass filter, attenuating signals near resonance. The peak voltage is 0.9062 volt. The output is stable with minimal frequency fluctuation. The FFT confirms reduced high frequency content. Lastly, with a pulse input, the circuit charges rapidly and smoothly to 1 volt with no overshoot. This highlights strong damping and fast energy setting. The FFT show a simpler spectrum compared to the series circuit, consistent with minimal ringing.
So I will talk about task 4, which we change the different value of RLC for series and parallel circuit. So we can see the formula that we derived just now at task 1. So for the second question, for the first question, we use the data that given by doctors, and the second question we changed the R from 1 ohm to 100 ohm. We can see that the coefficient for S has changed from 220 micro to 22 milli, and for HS it changed from S to 0.01 S for parallel. Yeah. So the next one is we change the R and L. We can see that the coefficient for S square it changed from 22 micro to 11 micro, while the S coefficient for S will remain 2.2 millisecond. And then for the HS, the S it changed from S to 0.1 S, and the 20 initially is 1, so it becomes 10 already. Becomes 20 already. So for the fourth question and fifth question, we also do some modification. Yeah, and then the result is shown there. And then for task 5, we talk about damping coefficient resonance radial frequency. We talk about the effect of resistance and inductance on damping and charging rate. So when the resistance is lower, the damping rate is less, while the resistance higher, the damping rate is small. So and then when the resistance is low, the charging rate is faster because more current flow, while the resistance is the higher, the charging rate is lower. So for inductance, when the damping rate is lower, when the inductance is lower, the damping rate become more. And then when the damping inductance is higher, the damping rate become less. While for charging rate, when the inductance is low, the charging rate becomes faster, while the inductance is higher, the charging rate becomes slower.
For task 6, the FFT analysis for series RLC circuit shows a dominant frequency as follows in the output for step signal. For sine signal, the dominant frequency with magnitude as shown in the output, and for pulse signal, it shows multiple frequencies with a dominant frequency. For parallel RLC circuit, the step signal is similar to the series RLC circuit. For sine signal also as well, and for pulse signal shows multiple frequencies with dominant frequency, similar to how the series circuit. For Fourier transform analysis, the transfer function characteristic equations and poles and damping as shown, with damping and steady state reaching at 0.1 seconds, and for parallel RLC circuit reaching at 0.05 with no damping.
For task 7, I will present the comparative analysis of series and parallel LC circuits in terms of capacitor charging behavior. Let's begin with charging speed. In series LC circuits, the inductor resists changes in current due to its LDIdt property. This resistance causes a delay in the charging of capacitor. In contrast, in the parallel LC configuration, the capacitor is directly connected across the voltage source, allowing it to charge faster with a minimal delay. Next is damping behavior. Using the parameter given in question, for the series LC, the damping coefficient alpha is 50 and the resonance frequency omega naught is approximately 213.2 radian per second. Since alpha square is smaller than omega naught square, this configuration is underdamped, which leads to oscillation. For the parallel LC, alpha is about 227.3, which means alpha square is larger than omega naught square, making it overdamped. That means no oscillation and it settles more smoothly. Moving on to stability, the series circuit is less stable due to its oscillatory response, while the parallel circuit is more stable with a smooth and monotonic transition to steady state. Finally, energy efficiency. The series LC wastes more energy to repeated oscillation and higher current in the resistor. Meanwhile, the parallel LC is more efficient as it avoids oscillation and minimizes energy loss in the resistor.
Before comparing the RLC circuit, let us define the key time domain characteristic. Steady state value is the final voltage the capacitor reaches after all transient effect die off. Rise time is the time taken for the voltage to rise from 10% to 90% of the steady state value. Setting time is the time required for the response to remain within 5% of the steady state value, while the overshoot measures how much the voltage exceeds the steady state value. Lastly, charging efficiency refers to how much energy from the source is actually stored in the capacitor, with the rest dissipated as heat. Now, looking at the series RLC circuit simulated in the MATLAB. These are the values simulated in the MATLAB. The steady state voltage is 1 volt, rise time and the setting time is short, the waveform shows oscillation with a high overshoot of 46%, and the charging efficiency is around 68%, which is relatively high, but some energy is lost in oscillation. In comparison, the parallel RLC circuit gives a more stable response. The steady state is again 1 volt, the rise time is slightly higher, and the setting time is shorter than in the series RLC circuit. There is no overshoot in this circuit, showing smooth behavior. However, charging efficiency dropped to around 31% due to more energy dissipated in the resistive part. This simulation value matches closely with our theoretical calculations shown in the report. This confirms that our MATLAB models are accurate and consistent with our analytic derivation using the transfer function and Laplace method.
Now, let's move on to task 9, where we summarize and compare the series and parallel LC circuits across 4 performance aspects. The first one is capacitor charging speed. The series LC charged the capacitor more slowly due to the inductor's resistance to current change and underdamped behavior, resulting in a longer setting time of 0.067 seconds. The parallel LC is more faster, setting in just 0.03 seconds because the capacitor is directly connected to the source and it isn't delayed by inductive effect. For the damping and stability, as covered earlier, the series RLC is underdamped and it exhibits oscillation, reducing the stability. In contrast, the parallel LC is overdamped and reaches steady state more quickly and reliably with no overshoot. For energy efficiency, the series configuration is less energy efficient because the energy is repeated exchanges and lost through resistor heating. The parallel LC conserves energy better with smoother transitions and minimal resistor losses. For frequency domain characteristic, the series RLC circuit acts like a bandpass filter. That means it allows energy at a certain frequency, called the resonance frequency, to pass through easily, while it blocks signals that are too low or too high in frequency. At resonance, the inductive and capacitive effects cancel each other out, so the circuit has a minimal impedance and the signal flows smoothly. For a parallel RLC circuit, it behaves more like a band-stop filter, also known as a notch filter. At its resonance frequency, instead of allowing the signal go through, it actually blocks the signal because the inductor and capacitor together create a low resistance path that diverts the signal away from the output. So to sum up, series RLC is a bandpass filter because it lets one frequency go through and block others. While for parallel RLC, it acts like a band-stop filter because it blocks one frequency and passes the rest. That's all. Thank you for listening to our presentation.